This is video 7E for the Year 11 Mathematical Methods course. In this video, we're going to cover the theory behind trigonometric equations under the topic of trigonometric functions. Specifically, we are going to explore what a trigonometric equation looks like, open and closed domains, the number of solutions to a trigonometric equation, how to solve trigonometric equations with no horizontal dilation, how to solve trigonometric equations with a horizontal dilation, how to use technology to solve trigonometric equations, and then we're going to cover some example questions. Now, over our last few years of maths, we've been looking at solving a variety of different types of equations. The first type was linear equations. In other words, equations of the form ax plus b is equal to 0, and what we found in this study is that we always had one solution to this equation. Then we moved on to quadratics, in which we were solving equations of the form ax squared plus bx plus c is equal to 0. And in this study, we found that we could have three different things that could happen. We could either have 0 solutions, 1 solution, or 2 solutions. And now, most recently, we've also had a look at cubic equations, which takes the form of ax cubed plus bx squared plus cx plus d is equal to 0. And in these situations, we found that we could either have 1 solution, 2 solutions, or 3 solutions. And so given this, I think it's safe to say that we've had quite a lot of experience at this point in solving different types of equations. And now we're going to be expanding this idea of solving equations into trigonometric equations. Or in other words, we're going to be solving equations that involve trigonometric functions. Now, as a very general case, we're typically going to be working with three different types of equations. We could either be working with an equation in the format of a multiplied by sine of b multiplied by x takes c plus d is equal to 0, or this exact same format, but instead of a sine function, we could be working with a cosine or a tangent function. Now, these are the typical cases that we're going to be working with. However, we will actually see that as we progress through this topic, we're actually going to come across some situations in which we're dealing with an equation that has different trig functions. So for example, you could be dealing with a situation in which you have 2 sine of x is equal to root 3 cos of x. So obviously a very different style of equation as the three that we've got over here, but we will have a look at different tactics in solving both these different types of equations. Now, before we actually get into the different processes involved in solving these types of equations, we need to make a very important differentiation between solving trigonometric functions compared to solving these types of equations up here. Now, as we clearly stated before, when we are solving linear equations, we can only ever have one solution. When we're dealing with quadratic equations, we can have 0, 1, or 2 solutions. When we're dealing with cubics, we can either have 1, 2, or 3 solutions, and we can continue this idea with different types of polynomials as well. But the key point that I'm trying to get across here is that whenever we're solving linear, quadratics, cubics, quartics, or whatever, we have a finite number of solutions. In other words, we always know that there is a maximum number of solutions to that particular equation. And so the really important differentiation here between these polynomial equations and trigonometric equations is the fact that when we have an open domain, in other words, when we can consider any real value of x as our solution, then trigonometric equations have an infinite number of solutions. And the reasoning for this is because of the periodic behavior of sine functions, cosine functions, and tangent functions, which, if you may recall, we've spent the last few videos talking quite a bit about. Because, if we may recall back to a few of our previous videos, we have the following identities when it comes to sine functions, cosine functions, and tangent functions. In that, sine of x is equal to sine of x plus 2k pi. We also have that cos of x is equal to cos of x plus 2k pi. And finally, we have that tan of x is equal to tan of x plus k pi. And in all three of these situations, k is just an integer. But what these three identities here communicate to us is that if we have either sine of x, cos of x, or tan of x, then all three of these values will be the exact same if we get x and then we add on an integer number of 2 pi for sine, an integer number of 2 pi for cos, and an integer number of pi for tan. And this is because sine and cos both have a period of 2 pi, in other words, the function repeats itself after every 2 pi, and then tan has a period of pi, so therefore it repeats itself after every pi. Now, just as a bit more of a solid example, let's quickly consider the equation of sine of x is equal to 0. Now, what I'm going to do to quickly illustrate this is draw out a standard unit circle. And if you recall what sine of x actually represents, it means that if we pick a particular point along this circle, then sine of x, where x represents the angle between the line connecting the origin and this point to the positive horizontal axis, tells us the vertical position of this particular point. So in other words, this height here. Then, given that, we have two situations in which we can have a point along the unit circle that has a vertical position of 0. Either this point here, or this point here. So if we consider what these 2 points represents, this point here represents when x is equal to 0, and then this point here, because we have a half revolution, tells us that x is equal to pi. But then furthermore, coming back to this first point over here, we can also say this correlates to when x is equal to 2 pi, because we do a complete revolution. So what that therefore means is that immediately we can consider three different solutions. We can say that x is either equal to 0, pi, or 2 pi. But then what happens if we want to go around the unit circle more? What happens, for example, if we go around the unit circle once, but then we go an extra half revolution? Then we get back to this point over here, in which case x is equal to 3 pi. And then what happens if we go around the unit circle once, and then we decide we're going to do it all over again? So we land back over here, in which case x is now equal to 4 pi. So it means then that we can actually extend out this answer. We can say that x is equal to 0, pi, 2 pi, 3 pi, 4 pi, and I'm sure you can guess what's happening here. We can just keep on going up by integers of pi. But the really cool thing is we can also do this in the other direction. So I'm just going to quickly draw out another smaller unit circle over here. So what we could now consider is if we do a half revolution in the backwards direction. So in other words, if we do a half revolution in the clockwise direction, so then we turn up over here. So again, this point here has a vertical coordinate of 0, so it satisfies what we're trying to find. And in this particular case, x is equal to negative pi. But then what happens if we do a full revolution in the clockwise direction? Then we land back over here, in which case x is equal to negative 2 pi, and so on. So what this therefore tells us is that we not only have to consider all the positive integers of pi, but we're also going to consider all the negative integers. So that involves negative pi, negative 2 pi, negative 3 pi, and so on. So this is just a very, very simple example of showing why trigonometric equations have an infinite number of solutions when we are considering an open domain. It's because of this periodic nature that after every single period, the unit circle repeats itself, and so therefore these trigonometric functions repeat themselves again and again and again every single time they go around the unit circle. And so it therefore makes sense that we have an infinite number of solutions because we can go around the unit circle as many times as we want. Now, of course, whenever we're actually solving equations, we can't actually write out an infinite number of solutions. The only way that we would be able to generalize this idea here is we would say that x is equal to k pi, where k is just an integer. Because that therefore captures all the positive integers of pi, it captures all the negative integers of pi, and it also captures 0. So this here would be the only way in which we could actually capture all these infinite number of solutions. However, most of the time we're not going to be working on an open domain. In other words, we're not going to be saying that x can be any value. Most of the time, we're actually going to be saying that x has to be within a set domain. So for example, if we consider the exact same equation that we had a look at up here, so in other words, sine of x is equal to 0, then we may consider this equation, but we would say that x can only be between 0 and 2 pi. And so what this therefore does is it limits what solutions we can actually consider to this particular equation. Because now in this case, if we only consider the solutions of x to be between 0 and 2 pi, then we can only consider these three solutions up here. In other words, 0, pi, and 2 pi. And so only by setting out a specific domain for the values of x can we have a finite number of solutions. Now this is going to be very, very important throughout the rest of this chapter because understanding whether you're working on a set domain or whether you're working on an infinite domain is a very, very important distinguishment to have. Because as soon as you start giving answers which are outside of this domain, you're going to start losing marks, which of course is something that we're going to try and avoid at all costs. Now, with that being said, let's go through a few different methods that we can implement to solve different forms of trigonometric equations. Now, the first two methods that we're going to look at are going to incorporate technology in solving these different trigonometric equations. So we're going to come over to our graphics calculator to solve this, but we're going to use two very, very different methods. The first of the two technological methods that we're going to be using is the graphics mode in our calculator. Now, out of the two methods which I'm about to show you, using the graphics mode in your calculator is arguably the weaker method, and I'll get into why that is in just a second. Now, in order to follow this through, we're going to actually go for an example of this. So we're going to consider the equation of 2 sine of x is equal to 1. And we're going to set the domain of this particular equation to be between 0 and 2 pi. Now, in order to solve this using your graphics calculator, here's what you're going to do. You are going to plot out the graph of the left-hand side of the equation. You will simultaneously plot out the right-hand side of the equation. You will then set the domain of your viewing window to match the same domain as in the original question. And then you will use this graphics mode to solve for the intersection points between the two different plots. And so then finally, the x-coordinates of these intersection points tell us the solutions of the equation. Now, with that being said, let us now open up our graphics calculator and use this method to solve this equation here. So we're going to come down to our graphics mode, and the first function that we're going to put in is the left-hand side of this equation, so in other words 2 sine of x. Then the right-hand side is just 1. Now we're going to execute this, and we're going to go shift viewing window, and we're going to set the domain between 0 and 2 pi. So 0 is our minimum, then 2 pi is our maximum. Execute this once again, and then we can go shift gsolve intersect, and so therefore we have one solution at x equals 0.52, and we have another one at x equals 2.1799. So therefore we can say the solutions are going to be x equals 0.52 and 2.62. Now, as you can probably guess, the main weakness with this particular method is that the graphics mode in our calculator does not give us exact values for the coordinates of these intersection points, because these two answers here of 0.52 and 2.62 are really just crude approximations of the actual exact answer. The true exact answers are pi over 6 and 5 pi over 6. But of course, using the graphics mode in our calculator will never allow us to actually get our answers in this format here. And it's not particularly obvious that 0.52 correlates to pi over 6, nor that 2.62 correlates to 5 pi over 6. So this is the key weakness with this particular method. It's a very easy method to implement, I'll give it that. However, in terms of getting the nice exact solutions, it's not going to be a particularly viable method, which is where our second technological method is going to be much more handy. And this is by using something called solven. And in order to demonstrate the use of solven, we're going to use the exact same equation as what we did with the first method, which is 2 sine of x is equal to 1, and this is for x being between 0 and 2 pi. Now, in order to use solven, this is what you are going to do. You are going to open up run matrix mode, and this is typically menu 1 for most calculators. Then you're going to follow the following prompts: option, calc, solven. Then what you are going to do is you are going to type in the equation that you were given. And then in order to indicate the domain of the solutions that you want, you type it in the following format. So after you've put in the equation, you put in comma, then you put in x, then you put another comma, then you put the lower bound, then another comma, and then the upper bound. And what this prompt here essentially does is it tells the calculator to only solve this equation between the values of the lower bound up to the upper bound, which in questions like this is obviously quite an important thing to consider. And then just by using that, it will actually spit out the exact answers to your particular equation. We're now going to jump back over to our graphics calculator and use solven to resolve this equation here. So we're going to go back to menu, and then we're going to go to our run matrix mode, so that is menu 1. We're then going to go options, calc, and solven is there. Now our equation is 2 sine of x is equal to 1. Then to set this domain, I'm going to put comma x, comma 0, because that's our lower bound, and then comma 2 pi, because that there is our upper bound. And now executing this, we get the two exact answers of pi over 6 and 5 pi over 6. And if you actually turn these into decimal answers, we get the exact same values as what we got when we solved it using the graphics mode. In other words, 0.52 and 2.62. Now, in my personal opinion, solven is realistically what you should always be using if you are allowed to use technology to solve these different trigonometric equations. The reason being is because, one, it's a very easy method to do it. You literally just have to type in the equation that you have and then put in the upper and lower bounds that you are given. And then secondly, you are given the exact answers. So no more are we going to be working with rounded answers. This method here gives us the exact solutions every single time. Now, the key thing about these two methods is that both of them have a key strength of being very easy methods to implement. Both of them just require you to put in the equations as you're given them, and then to make sure that you specify the upper and lower bounds of your domain. However, the only problem is this. Most of the time in tests or exams, you will be expected to solve these equations using an algebraic method. Now, with that being said, I'm still going to highly encourage you to use either one of these two methods, most likely solven more than anything else, to double check your answers because of how easy it is to actually get the exact answers. However, most of the time, you're going to have to use an algebraic method of solving these equations rather than just outright using technology. So what we're going to spend the next bit of time going through is how we can solve these equations using algebra. Now, when we are dealing with using algebra to solve these different trigonometric equations, we're going to be considering two different types of equations that we're going to be working with. One of which is going to be significantly easier to manage than the other, but they'll both still take a very similar approach. Now, as we previously looked at before, when we're working with trigonometric equations, we're typically working with three different types. For our first discussion with the more simplistic type of trigonometric equations, we are only going to consider equations of the following form. So in other words, we have a multiplied by sine x, cos x, or tan x plus d is equal to 0. Now the key thing that you'll notice about these three equations here are the fact that x is just by itself. It does not have any coefficient and it doesn't have anything being added or subtracted from it. So when we're looking at this first type of question here, keep in mind that this will only work when x is all by itself, whether it be a sine function, a cosine function, or a tangent function. Now, the approach that you're going to take for these ones here is the following. You are first of all going to rearrange the equation to either get sine x, cos x, or tan x all by itself. So in other words, we want to rearrange the equation to get it in the form of sine x, cos x, or tan x is equal to some number. Then, step number 2, you are going to use the unit circle to solve for the value of x for one revolution around the unit circle. So in other words, we're going to use the unit circle to only solve this equation for x being between 0 and 2 pi. So in other words, just through one revolution of the unit circle. And then the third and final step is we're going to use the fact that sine, cos, and tan are all periodic functions to then solve for all the solutions in the given domain that you have. Now, in order to do this last step, we have to recall the fact that sine of x and cos of x both have a period of 2 pi, whereas tan of x has a period of pi. So therefore, if we want to solve for all the solutions of sine x and cos of x, we're going to keep adding or subtracting integers of 2 pi until we reach the upper and lower bounds of our domain, and then with tan of x, we'll either add or subtract integers of pi until we reach the upper and lower bounds of our domain. So as I just said, we're going to keep on adding or subtracting multiples of 2 pi for sine and cos, or multiples of pi for tan, to the solutions of step number 2, so in other words, the solutions for just one revolution around the unit circle, until we reach the upper and lower bounds of the given domain. Now, just as a quick thing here as well, when we are going about implementing step number 2, we need to recall the fact that sine is the vertical position of the point around the unit circle, cos is the horizontal position of a particular point around the unit circle, and then tan is equal to sine over cos, or in other words, it's the tangent of the line from the origin up to that point. And so when we're actioning step number 2, we need to be very, very careful, depending on whether we're working with an equation that has a sine, cos, or tan function, to make sure that when we're looking at the unit circle, that we're looking at the correct coordinate. And again, sine is for the vertical position, cos is for the horizontal position, and then finally tan is for the vertical position divided by the horizontal position. And then finally, step number 4 is to list out all of your solutions in ascending order. So this is the 4-step process that you're going to use when you are dealing with equations of this format here. Now again, this definitely is the more simple type of question out of the two that we're about to have a look at, but it's definitely a good process to still keep in mind. Now, with that being said, let us now go through a few different examples of implementing this 4-step process. So the first example that we're going to have a look at is for the equation of 2 sine of x is equal to 1, and for this particular equation, we only want to solve for x being between 0 and 2 pi. And so the first thing that we're going to do here is get this sine of x all by itself. To do that, we can just divide both sides by 2. So now we have sine of x is equal to 1 over 2. And so what we're going to do now is use the unit circle to find all the points around one revolution that have a vertical coordinate of 1/2. And again, the reason why we want the vertical coordinate to be 1/2 is because we have sine. And so by using the unit circle for this, we find that x is going to be equal to pi over 6 and 5 pi over 6. Now the nice thing about this particular equation is the fact that we're only being asked to solve for this on the domain of 0 up to 2 pi, which again is just one revolution around the unit circle. So we've just found the two solutions for this particular equation. Let's get into a slightly more challenging one. We now have 2 cos of x, take root 3 is equal to 0, and we're now going to consider the domain of x for being between 0 and 4 pi. So again, the first thing that we're going to do here is isolate this cos of x. The way that we can do that, we can add root 3 onto the other side, and then we can divide both sides by 2. And in doing that, we then get cos of x is equal to root 3 over 2. And so now we're going to use the unit circle to find all the points around one revolution that have a horizontal coordinate of root 3 over 2. And the reason why we're only considering the horizontal coordinate in this particular case is because we've got cos. Now, using the unit circle, we have 2 points which have a horizontal coordinate of root 3 over 2, and that is when x is equal to pi over 6 and 11 pi over 6. And so now, because we're dealing with the domain of 0 up to 4 pi, we are going to keep adding on 2 pi to these answers until we reach the upper limit of 4 pi. So, first things first, if we add on 2 pi to both of these solutions here, we get 13 pi over 6 and 23 pi over 6. If we then add on a further 2 pi, then we get 25 pi over 6 and 35 pi over 6. Now the problem with both of these solutions here is the fact that they are above the upper bound of 4 pi. So what that therefore tells us is that we cannot consider these two solutions because they lie outside of a domain that we're trying to solve this equation for. So what this therefore tells us is that these 4 solutions are the only solutions to this equation that satisfy this particular domain. So our final answer will be pi over 6, 11 pi over 6, 13 pi over 6, and then 23 pi over 6. And now the third and final example we're going to consider here is for root 3 tan of x is equal to 1. And we are going to consider this on the domain of x being between positive 2 pi and negative 2 pi. Alrighty, so the first thing that we're going to do here is isolate this tan of x. Doing so, we get tan of x is equal to 1 over root 3. And now we're going to use the unit circle to find all the values of x around one revolution, such that tan of x is equal to 1 over root 3. And in order to do this, we need to get all the vertical coordinates of the points around the unit circle, and then divide them by their horizontal coordinates. Because that will then tell us the tan of a particular point, and if we do this for one revolution around the unit circle, we find that x is equal to pi over 6 and 7 pi over 6. And now we want to extend these answers all the way down to negative 2 pi. So these here are the answers from x being between 0 and 2 pi. We now need to go all the way down to negative 2 pi. And the way that we're going to do this is we're going to keep subtracting these answers by pi until we reach the lower bound of our domain. The reason why we're subtracting pi is because pi is the period of 10. So by subtracting both these answers by pi, we get negative 5 pi over 6 and pi over 6. And then by subtracting them both by pi again, we get negative 11 pi over 6 and then negative 5 pi over 6. And then subtracting by pi again, we get negative 17 pi over 6 and negative 11 pi over 6. Now, we cannot consider this answer here because this now goes below this lower bound of negative 2 pi. So we can't consider this one here. So that therefore tells us that we can only consider these sets of answers here as the solutions to our particular equation. Now, what you should hopefully notice straight away here is that a lot of these answers are just double ups of each other. So in other words, we've got pi over 6 here and pi over 6 here. We've got 7 pi over 6 all by itself. We've got negative 5 pi over 6 and negative 5 pi over 6 here. And we've also got negative 11 pi over 6 and negative 11 pi over 6 here. So what that therefore tells us is that x is equal to negative 11 pi over 6, negative 5 pi over 6, pi over 6, and 7 pi over 6. And so that there is how you use algebra to solve these more basic types of trigonometric equations. What we're going to have a look at now are the more challenging types of questions. When we are now considering these harder types of questions, essentially all we mean is that we're now going to be solving equations of this particular format. And so what you should hopefully notice here is that the only difference between this type of question and the type that we just considered there is the fact that now we're going to have a coefficient of our x when it comes to the sine function, the cosine function, and the tangent function. And believe it or not, this one extra number drastically changes how you need to approach these different types of questions. However, there is a nice thing about this in that a few of the steps will be very, very similar to what we just did with this type of question up here. However, there are a few key distinct differences that we need to be very, very mindful of. Now, the step-by-step process needed to solve these types of equations here, let's go through that right now. So, the first step is identical to our previous process in that we need to rearrange our equation to get the sine, cos, or tan all by itself. So in other words, we're just going to rearrange the equation to get it in the format of sine of bx, cos of bx, or tan of bx is equal to some number. Now, step number 2. This is where things get a little bit different. We need to define what I like to call your new domain. Now, essentially what this comes down to is this. If we have that x must be between two different values, let's call these values m and n, then if we consider b multiplied by x, then the domain of b multiplied by x is b multiplied by m and b multiplied by n. So in other words, you should notice all that we've done here is we multiplied through everything in this inequality by the value of b. And so this here is what is called your new domain. And this will ultimately depend on whatever the coefficient of x is in your original question. Then, step number 3. You are now going to find all the solutions for your equation in this new domain. Now this step here is actually combining two different steps from our previous process, so just in case if you need a bit of a reminder. So the first thing that you're going to do here is use the unit circle to find all the solutions around one lap of the unit circle. And then you are going to use the periodic nature of sine, cos, and tan to find all the solutions in your new domain. And just in case you need a reminder as well, when you're dealing with the sine and cosine functions, that means that you can add or subtract integers of 2 pi, whereas when you're dealing with tan, you can add or subtract integers of pi. And so then once you've found all the solutions in your new domain, you're going to have your solutions in the following format. That b of x is equal to all the solutions that you just found. And then to get x all by itself in this equation, you'll then divide through everything by this value of b. And so that there is the 4-step process that you're going to have to implement in order to solve these more challenging types of trigonometric equations. As I made mention of before, some parts of this process are identical to the process with the easier types of equations. However, there are a few key differences that are essential to implement when you're doing questions like this. Mainly when it comes to this idea of having your new domain. Now, in my personal experience, this is best shown through practice. So let's now have a look at a few examples of using this second process. The first example that we're going to consider is sine of 2x, take 1, is equal to 0, and we're going to solve this on the domain of 0 up to 2 pi. So, first thing we're going to do here is isolate this sine function by adding 1 onto both sides of the equation, and in doing so we get sine of 2x is equal to 1. What we're going to do from here is define our new domain. So because we know that x must lie between 0 and 2 pi, then we therefore know that 2x must lie between 0 and 4 pi. And all we've done to get from this original domain to this new domain is we've multiplied everything by 2. Now we want to solve this equation on this domain. And so the way that we're going to do this is by solving this equation for one revolution around the unit circle, and then we'll expand these answers from 0 up to 4 pi. So by using one revolution around the unit circle, we know that the only solution for this equation will be when 2x is equal to pi over 2. But now we want to expand this from 0 up to 4 pi, so the way that we're going to do this is we're going to keep on adding 2 pi until we reach the upper bound of our domain. And again, the reason why we add on 2 pi is because sine has a period of 2 pi. So if we add 2 pi to the solution, then we get 5 pi over 2. Then if we add on a further 2 pi, we get 9 pi over 2. Now the only problem with this last answer here is that 9 pi over 2 is greater than 4 pi, which means that it does not fit in our new domain. So therefore we cannot consider this answer here. So the only two solutions that we have to consider are these two here. So let's just quickly write this out in a nicer format. So we can now say that 2x is equal to pi over 2 and 5 pi over 2. And so now to get this x all by itself, because at the end of the day that's what we're trying to find, we're going to divide everything through by 2. And in doing so, we then get x is equal to pi over 4 and 5 pi over 4. So those are our two answers for this particular equation, and a really good habit to get into here is making sure that both these answers lie within the original domain of the question. Because if you recall, the original domain of the question was x must be between 0 and 2 pi, and we can very clearly see that both these answers lie between 0 and 2 pi. So if you had any answers that lied outside of this original domain, then it means that you've done something wrong and you need to go back and find out what's happened. But in this particular case, we're all good to go. The second example that we're going to consider is the following equation. 2 multiplied by cos of 3x is equal to 1. And we're going to consider this on the domain of x being between 0 and pi. So, once again, first thing that we're going to do here is isolate this cos of 3x. We can do that by dividing both sides by 2. In which case we get cos of 3x is equal to 1 over 2. And now we have to define our new domain. So in this particular case, we're now dealing with 3x, so I'm going to put 3x here, which means then that our new domain is going to be from 0 up to 3 pi. And the way that we've done that is we've just multiplied everything in the original domain by 3. And so now we need to solve this equation over this domain. And so if we first of all solve the equation over one revolution of a unit circle, then we get answers of pi over 3 and 5 pi over 3. And now, in order to extend these answers into the entire domain that we're considering, we're going to keep adding 2 pi to these answers until we reach the upper bound of our domain. And again, the reason why we're adding on 2 pi is because cos has a period of 2 pi. So if we add on 2 pi to both these answers, then we get 7 pi over 3, and we get 11 pi over 3. And now the only problem that we have here is that this particular answer is greater than the upper bound of our domain. So it means that we cannot consider this answer here, but these 3 here are absolutely fine. So now let's write this out in a more list format. So we have 3x is equal to pi over 3, 5 pi over 3, and 7 pi over 3. And so now finally, in order to get this x all by itself, we're going to divide through everything by 3. And in doing so, we now get x is equal to pi over 9, 5 pi over 9, and finally 7 pi over 9. And now, just as a quick final check, we want to make sure that all the answers that we have here lie in the domain that we are originally given, which for this particular question was between 0 and pi, and we can see that all 3 of these answers are greater than 0 but less than pi, so we are good in that respect there. And that there is how you solve trigonometric equations using both technology and algebra. These techniques here are going to be very, very important throughout the rest of your trigonometric journey, whether it be throughout the rest of year 11, but also when you enter year 12 as well. So practice this technique as much as you possibly can and make sure that you become very, very competent at this particular process. It will be very, very helpful moving forwards. Alrighty, let's wrap up. So in this video, we introduce trigonometric equations, which can take the appearance of any of these equations here. Sometimes we can even see equations where two of these trig functions appear simultaneously. When solving these equations on an open domain, or in other words where x can be any real number, then due to the periodic behavior of trigonometric functions, we will have an infinite number of solutions. However, if we limit the domain of x, then we have a finite number of solutions. To solve equations without any horizontal dilation, or in other words when b is equal to 1, then we have to use the unit circle to solve for one revolution around the unit circle, and then use periodic behavior to find all the solutions in the given domain. To do this, it is important to recall the definitions of sine, cos, and tan in relation to the unit circle. To solve equations with a horizontal dilation, or in other words when b is not equal to 1, then we must define a new domain to solve and manipulate the equation on. To do this, we recall that if x lies between m and n, then bx must lie between bm and bn, where b is a real number. We saw how we can utilize different applications of technology to solve these equations, including graphing and then also using solven. Finally, we applied these strategies to solve some exam-style questions. And that's it for now. See you in the next video.